A permutation is a selection of objects where order is important. A selection of objects where order is important. And I'm going to come back to the example. I just want to go down to combination and give you the definition of that to compare. A combination is a selection of objects Anybody want to guess at the end of the sentence where order is not important? Turn to someone sitting around you and tell them your postal code. Did anyone have the same postal code? Yeah, because it's by region. So R is Manitoba, and then it goes by area of the city, by street, and then everyone on the same street with even and odd have the same postal code. So it's done. Point of that is, if you took your postal code and rearranged the digits or the letters or the numbers, it doesn't matter. So if I just put any random of your 6 letters on an envelope addressed to you, is it going to get to you? Maybe, maybe not. What about your phone number? So if I texted you and just randomly put the 7 digits in a different order, does that matter? Yes. So there's things in life where the order matters. What about license plates? If I just randomly mix them up, is that the same license plate? These are all examples of permutations. So postal codes. Phone numbers. License plates. And so you might be thinking, wow, there's a whole branch of mathematics devoted to this. Well, yes, somebody has to care about this stuff. Last year, maybe the year before, what happened when you suddenly needed to phone or text a number? I think it was last year. Could have been the year before. You suddenly had to put the area code. Why? Because it's dumb. But there's got to be a reason, right? They don't just have us put 3 extra numbers for no reason. So why did MTS or whoever's in charge of that decide we suddenly have to put the area code? We're running out of numbers. So eventually there's going to be 2 area codes in Manitoba so that they can recycle the same digit, 7-digit numbers. Who knew we were running out of numbers? Well, that's the mathematician's job to figure out how many numbers are out there. If you think of a city like Toronto, they have 4 different area codes. So if you don't put the area code, you could reach someone in a different part of the city than what you're intended to just because they have the same 7-digit number. That's what this branch of mathematics deals with, is knowing how many combinations or permutations there are of postal codes, of phone numbers, of license plate, that kind of thing. Okay, what's an example of a combination? Hands of cards. If you have 3 kings and 2 queens in a hand of cards, does it matter which way you physically arrange them in your hand? Does it matter if you put the kings before the queens? Does it matter if you put the queens before the kings? If you alternate them, does it change your poker hand? That's a combination. So example, if I put the 3 kings first and then the 2 queens, or I decide to alternate them, or I decide to put the queens first because women should come first. Doesn't matter. That's still a full house. Doesn't matter how you arrange them in your physical hand. That's a combination. What's on your locker? A lock. And what does a lock have? Oh, does it? This is where we've lied to you. Is it a lock or combination? Can you take those three numbers and put them in any order and the lock's going to open? Or does the order matter? It's not a combination, it's a permutation. Sorry. What about a McDonald's combo? Does it matter the order they put the ingredients of the combo on your tray? If they give you the drink before the fries, before the Big Mac, is that a different combo if they gave you the fries first? What if they put the Big Mac on the tray first? So that actually is a combination. We would not mix with McDonald's. We would not touch that. Lockers, yep, we did lie to you on that one. It's actually a permutation. So now that you know the two definitions, we're going to focus just on permutations first. Because when the order matters, there's a lot more work that goes into it when the order doesn't matter. And we're going to jump right in with an example. And this would have been like a logic question, like about grade 5 or 6. The new Bomber Stadium has 5 gates. In how many ways can you enter, then leave the stadium by different gates? Turn and talk. Lots of good conversation happening. Lots of logic stuff. It's interesting to me to watch you because I can tell right away who the visual people in because they have people going in with their hands and people coming out and they're pointing. Those are the visual people. You can tell them right away. So again, this would have been a logic problem in grade 5. Well, now here's the actual math behind it. To solve these types of questions, we use, this might be the most important formula sounding name ever, the fundamental counting principle. The fundamental counting principle. If I were to name a theory, it would have the word fundamental in it because it sounds so important. Bless you. We call it the FCP for short because words scare us. And the fundamental counting principle says this. If one task can be performed in A ways, and a second task can be performed in B ways, then the two tasks can be performed in A times B ways. That is the fundamental counting principle. If one task can be performed in A ways and a second task can be performed in B ways, then the two tasks can be performed in A times B ways. Grabbing my paper. So with permutations, well, and combinations, we're going to talk about choices. And in this question, there's 2 choices you need to make. You need to choose a gate to go in, and you need to choose a gate to come out. And so we use blanks to represent choices. I'm not always going to write what the blanks represent. I'm just doing it at the beginning to help you understand what's going on. So this will be the number of ways to enter. And this will be the number of ways to leave. I forgot the word ways. To enter. Number of ways to leave. Again, I won't usually write this stuff down once we get into the questions, but I just want you for the first few to understand what the blanks represent. So you arrive at the Bomber game, there's 5 doors to go in, that means you have 5 different ways you can choose how you want to enter. The problem is when you come out. Why are there not 5 ways to come out? It has to be different. So how many choices do you have to come out? You have 4. The fundamental counting principle says that we multiply these. Now let's talk about this multiplication. And I want you to think of the word and. because later I'm going to add the word or, which means something different mathematically. And always means multiply. So do you need to enter and leave, or do you need to enter or leave? And those two words are going to become important in a couple examples from now. Do you need to enter and leave, or enter or leave? And, that's why we're multiplying. 5 times 4 is 20. When you were discussing with your partner, how many came up with 20? Good job, good job. There's your first permutation. Example number 2. How many 3-digit numbers are there? What's a digit? Does a digit always mean the same thing as a number? Okay, so what's the difference between a digit and a number? One number and a group of numbers, I like that. So a digit really has 2 different meanings. Number 1, it can be a placeholder within a number. So the tens digit, the hundreds digit, the thousands digit, so it's one place value. Or a digit can be a single number, so between 0 and 9. So it just depends on the question what we're looking at. Either way, we use blanks to represent choices. And what do we need to choose here? We need to choose 3 different digits. The first blank will represent the first digit. Second will represent the second digit. And the third, I know it's shocking, will represent the third digit. You don't need to write this down. If I give you the number 120, how many digits does it have? 3. What if I gave you 1,476? How many digits does it have? What if I gave you the number 019? How many digits does it have? We don't actually count this as a 3-digit number. We count this as a 2-digit number. Because I could put infinite number of zeros in front, and it's not changing. This is still 19 of something. So when we think of the first digit, what it's telling you is it can't be a 0. That wouldn't make a 3-digit number if you put a 0 in the front. How many choices do we have for this first blank? Well, how many digits are there between 0 and 9? So that's 10. If we can't have 0, how many choices? 9 for the first one, because we can't have 0. Can we have 0 as a second digit? So there are 10 possibilities for the second digit. Can I have a 0 at the end of a number? Sure, so 10 possibilities for the last. Do we need a first digit or a second or a third? Or do we need a first digit and a second and a third? And means we multiply. These would all be non-calculator questions so far. So again, when you're multiplying numbers, we've talked about this before, don't feel you need to do them in order. Grab whatever your brain sees first. My brain sees the 10 times 10, and then I times by the 9. If your brain sees a 9 times 10, great, whatever you see first. Either way, when you multiply these 3 numbers together, we get 900. 900 3-digit numbers. What's the point of the fundamental counting principle is to now know there are 900 of them without having to list out all 900. Imagine if the only way we had to figure out how many 3-digit numbers there were to list them all out. Would you want to list 900 of them? I would not either. That's the point of the fundamental counting principle. It's just a quick way to count something out without having to list it all out. So we're going to do what's called permutation with restriction. So ladies, and I'm being a little sexist, but it's probably true. Ladies, at some point you might be planning your wedding, and it's usually a girl thing, so that's why I'm leaving the guys out. And what's going to happen is you're going to come to the seating plan. And typical weddings have about 200 people, so you need to seat 200 people, usually around round tables. But what happens is somebody has to sit with somebody, and then these people can't sit with these people, and no one wants to sit with Grandma because she gets drunk, and then Uncle Fred, he's weird, so no one wants to sit with him. But then these people have to be on the right-hand side of the table, and you get all these different restrictions. That's what permutations with restrictions are. It's when there's a condition that's going to limit the number of total possibilities. So what you're looking for are things that start with, must end with, must sit together, must not be together, etc., etc. So I've grouped the remaining examples together. Example number 3 is what I'm going to call seating problems, because it all revolves around seating people in different situations. So these are seating problems. Number 4 are called digit problems. And then number 5 are number problems. And we've already talked about what the difference between a digit and a number is. So seating problems, digit problems, number problems are the 3 main ones that we're going to talk about. So example 3, imagine there are 5 people, including Jack and Jill, who want to sit in each of the following arrangements. We're going to put them in 5 seats, in 3 seats, in 6 seats, in 5 seats, but Jack must be in the first seat, in 5 seats, but Jack must be in the middle. Then Jack's like, no, I want to be on the end. Then Jack and Jill have to sit together. Then they break up and they don't want to sit together. And we're going to look at all the different ways we can seat all these people in all these circumstances. So example number 3A. 5 people, 5 seats. How many blanks do you think we're going to draw? 5. And just because I draw them horizontally doesn't necessarily mean these people are sitting side by side. This could represent a row. So if you look in this room, these 4 rows have 5 desks. So this just could be a row of 5 desks. It doesn't mean they have to be seated in a horizontal row. It could be vertical. First person walks in. How many desks do they have to choose from? 5. They pick a desk. They sit down. The next person walks in. How many desks do they have to choose from? 4. They pick a desk and they sit down. The third person walks in. They have 3 choices. The second person has, and the last person has. Now, do we need to sit the first person or the second or the third or the fourth or the fifth? Or do we need to seat the first and the second and the third and the fourth and the fifth? So this is going to be multiplication. Again, multiply what your brain sees first. My brain grabs a 5 and a 2 because I know that that's 10 and that's easy to multiply. Then I would do the 4 and the 3, which is 12. So then I would do 10 times 12 is 120. That's 1 row of 5 people, 120 different ways to seat them. Imagine you have 6 rows of 5 people. So when you're like, oh, that teacher's picking on me. No, we're not. There's so many different seating plans. It just worked out that you're where you are. We don't take that into account. We just seat you. 1 row, 120 different possibilities. Okay, let's mix up the situation. 5 people still, 3 seats. What's the implication in the question? What's the assumption? After we have seated 3 people, what's the assumption? 2 are not seated. They're not going to get a seat. So they're not sitting on laps. That's weird. Only 3 people are going to get a seat. So 3 blanks. How many people can we choose for the first seat? How many people can we choose for the second seat? How many people can we choose for the third seat? What about those other people? We don't care. We have filled our 3 seats. We don't care where they go or where they stand. Offer of 60? So think about that. By taking away 2 seats, I've cut the possibilities in half. So by taking away less than half the seats, I've cut the possibilities in half. How did I know to draw 3 blanks and not 5 blanks? Well, what's going to happen if you started with 5 blanks? You're going to say the first person walks in and they have a choice of 3 different desks or 3 different seats. And then the second person walks in and they have a choice of 2. And the first or third person walks in and they have a choice of 1. How many choices does the fourth person have? None and none. And what's going to happen when we multiply these? You get 0, and that doesn't make sense. That's why I didn't start with 5 blanks. When you have groups of something and one is lower, so we had 3 desks and 5 people, always go for the lower number of blanks. Always go for the lower number of blanks. Otherwise, you're going to run into this, and we know that doesn't make sense. So does this represent people or does this represent seats? So you can just think of the choices. This is seats. This is people. So the first desk, how many people could sit in it? 5, right? The second desk, how many people could sit in it? 4, and then 3. The problem, if you do it this way, you're going to end up 0, 0. And we know there's not 0 ways. That doesn't make sense. We know there's some kind of order to it. Okay, let's put more desks than people. So still 5 people, but now we're going to put 6 desks. So we're in rows 1 and 2 over there. The assumption is 1 desk is going to remain open, and we're okay with that. So 5 people, 6 desks, which is the lower number. So we're going to draw 5 blanks. First person walks in, how many choices do they have? Second person walks in, how many choices do they have? Followed by, followed by, followed by. Do we add them or do we multiply them? Multiply them according to the fundamental counting principle. Now, using your mental math skills, use A to figure out C. How did you know so quickly it was 720? So all we added to this was times 6. So I just took the 120 times 6. What's 12 times 6? 72. We added one more desk. Look at the possibilities here. By adding one desk, we went from 120 different seating plans to 720 different seating plans. How are we doing so far? Okay. D is 5 people, 5 seats. Jack must be in the first seat. 5 people, 5 seats. Doesn't matter, we're drawing 5 blanks. I'm going to show my work by writing down the condition, and the condition is Jack has to be in this first desk. That's showing your work. That's it. That tells me that you're showing what's going on there. How many people can sit in this first desk? 1. Only Jack can sit there, so there is one possibility. He sits down. The next person walks in. They're not as fussy. They don't care where they sit, so how many people can choose the second desk? Followed by, followed by, followed by. I heard 24. 200. 24. So look what we did here. By fixing one person, by one person needing a seat, we dropped from 720 to 24. E. Jack must be on the end. The problem is, which end? If we think of this as a horizontal row, so like a movie theater, is he on the left or is he on the right? We don't know. So what we're going to do is 2 separate cases. We're going to do case 1 and case 2. Case 1 will have Jack on the left-hand side. Case 2 will have Jack on the right-hand side. I skipped one, didn't I? This is F. Let's come back to E. I was so excited about Jack. No wonder you were all looking at me like that. Do you understand the difference between Jack being in the first seat versus Jack being on the end? Turn and tell your partner or someone around you what's the difference between those. Jack being in the first seat, Jack being on the end. Jack shouldn't be so picky. Seriously, Jack. Jack is a pain in the butt. Okay, case number 1 is actually the same that we did above. There's one choice for the first desk. Nobody else is being fussy, so it's going to be identical to be 24. What about case number 2? So seat the restriction first. So let's fill in Jack's position first. How many choices for the last desk or the one that's on the right? Does it matter who sits way over here on the left? Number of choices, followed by, followed by, followed by. Take a look at the numbers. Use some logic here. What does it have to equal when we multiply? Now we just need to figure out what do we do with these 2 cases. Is it Jack is on the left or Jack is on the right? Or is it Jack is on the left and Jack is on the right? So this is the first time we're seeing this word or. What or means mathematically is add. And means multiply, or means add. So there's 24 possibilities in the first case and 24 possibilities in the second. The total number of possibilities, 48. or and are going to become very important in this unit because it changes what you're doing mathematically. How about now we go back to E? 5 people, 5 desks, Jack has to be in the middle. How many blanks? How do we show the work to show the restriction? So underneath the middle desk, I'm going to put Jack. Assuming there's only one Jack. What about this first desk? Now, what if I hadn't chosen to fill the first desk first? What if I had chosen to fill the last desk first? Why does it not matter? So let's say I'd chosen to start back here. How many people would have had here? And then, and then, and then. So does it matter where I put these numbers? What if I'd chosen to fill the second desk first? Doesn't matter. The total number of permutations when Jack is in the middle is 24. Show me your thumb. How are we doing so far? Getting it, kind of getting it, not getting it. Good. 5 people, 5 seats. Jack and Jill must be together. How many blanks? I'm going to circle just to show that Jack and Jill are together. Does it matter who is first? Does it say Jack has to be first? Jill has to be first? Doesn't matter. So how many choices for this first seat? 2, Jack or Jill. How many for the second? Okay, they're together. Everything's good. What about this seat? Does it matter who's sitting beside them? How many choices? Offer of 12? Confirm? But that only puts Jack and Jill in the first and second seat. Do they have to be first and second? No. What's the next case? Second and third. So again, the bubble I just used to show people that need to be together. How many choices for the first blank in that bubble? 2, and then? How many for the very first seat, because no one else cares beside Jack and Jill? And then? And then? Marjorie, wake up, wake up, wake up. Case number 3. What numbers are going to go in the bubble? 2 and 1. What numbers are going to go in the remaining blanks? Doesn't matter. 3, 2, 1. But that's only 3 cases. What's the 4th case? What numbers go in the bubble? What's the 5th case? No, just kidding. There's no 5th. How do we know we're done? Because they're at the end of the row. What do I do with all these cases? Am I multiplying or am I adding, and why? Why am I going to add? Because it's or. It's either case 1 or case 2 or case 3, so plus, plus, plus. I think I heard it, but I'm not sure I heard it. That's the long way. I'm going to show you the short way, and you can pick whatever way you want. Short way, I'm just going to write down the first case. So typically we put them in the first and second spot, and then we fill in everything else the way we normally do. And in order to do all the cases at one time, I'm going to take the remaining people, and I'm going to multiply by 1 more. So the highest is 3. 3 plus 1 gives us 4. How many cases did we have up here? 4. That's where it's coming from. Let's imagine I had 7 people in total. So I would have had Jack and Jill. How many remaining people would I have had from 7? 5, and I would have multiplied by 6. So this is always remaining people plus 1. Can't spell remaining. Remaining people plus 1. What that does is does all 4 cases at the same time. If your brain likes to see the cases because it's your visual and you need to write it out, fine. If you can see the short way, fine. Completely up to you. Either way, if you were to multiply this out, you would get 48. Look how much work it is when people have to be together. Okay, what if they don't want to be together? So Jack and Jill break up. They cannot sit beside each other. Now what? Here is a deep philosophical idea. You're either sitting next to someone or you're not. You're either sitting next to someone or you're not. Are there any other possibilities? No, it's very deep, very philosophical. So Maddie is either sitting next to Casey or she's not. There's no other possibilities. So the way we're going to do when people don't have to be together is we're going to take what we call the total amount of permutations, and what that means is anyone sits anywhere, no restrictions, and we're going to minus off when they are together. If we take anyone sitting anywhere and we minus when they are together, what does that have to equal? So if we take any restriction, anyone sitting anywhere, nobody cares, and we subtract all the cases when they are together, what does that have to leave us? When they're not together. So we're going to take what we call the total, and what that means is no restrictions. And we're going to minus when the people are together. And that has to equal when they're not together. This is the easiest way to do not together because the cases are astronomical. They could be in the first and the third, the first and the fourth, the first and the fifth, the second and the fourth, the second and the fifth. They could be the first and the third. They could be the third and the fifth. And to try to do all those cases, it just gets way out of whack. This is the easiest way to do it. So what does the total mean, no restrictions? That's just 5 people, 5 seats, no restrictions. Anyone can sit where they want. How many people could sit in the first seat? And then 3, and then 2, and then 1. So that was actually what we did in part A. That was our no restriction. Anyone sit anywhere. And what did we say the answer to part A was? When they are together, we just did above. So we circle 2 and 1, 3, 2, 1. And then if we're doing it the short way, we just add the smallest plus 1, which would be that times 4. That does all 4 cases in the same time, which we just said, which was 48. So how many ways are they not together? That's the easiest way to do things that don't have to be together or don't want to be together, is do the total no restriction minus when they are together. Otherwise, you have to list out every single possibility, and you're bound to miss one when there's 72 of them. Questions so far? This is where you just say, Jack, Jill, suck it up, sit next to each other. We don't care. Okay, let's leave Jack and Jill. Let's go on to what I call the digit problems. You need to create a 3-digit PIN for your bank card. Number 1. Do not say PIN number. That drives me crazy. What does PIN stand for? Personal Identification Number. So if you say a PIN number, you are saying personal identification number. It is just a PIN. Number 2, do not bank somewhere where they have a 3-digit PIN. Just don't bank there. Why not? Because it's really easy to crack. We're going to see in a second how many possibilities and how many times if someone stole your bank card, they would just have to randomly punch in numbers to figure out your PIN. So do not bank anywhere that they're asking you to do a 3-digit PIN. Most are 4, now they're going to 5 because it's even harder to crack. You can only use the digits 1, 2, 3, 4, and 5. Highlight or circle the word only. Do not bank somewhere when they're only giving you 5 possibilities for your pin, because that's even easier to crack. What does the only mean? It means only. You only have those digits. Can they repeat? So could you have the pin 333? Sure. Well, it would be too easy, but it's a possibility. Could you have 552? 114? Yes. So if the question doesn't talk about repetition, we assume we can have repetition. How many different pins can you create? How many blanks? How many choices do you have for the first blank? How many do you have for the second blank? How many do you have for the third blank? Why with the people did we decrease by 1 every time and now we're not? Because people you can't repeat. Even if they're twins, they are different people. So I can't clone Leah and put her in 6 different desks. It doesn't work that way with people. With digits, we can absolutely repeat them, okay? So people are never repetition, that's why it's going down. 5 times 5 times 5, how many different pins? Yeah, don't bank there. Just please don't bank there. Or don't lose your card. That's no restriction. Okay, that's just a normal 3 digits, no restriction. Let's start the restriction questions. It has to start with a 3. How many blanks? We need to show some kind of work that shows the restriction. So we put Jack or we put a little J. All I'm going to put here is a 3 because the 3 has to be first. How many 3s do we have? We have 1 of them. Now, where your brain's going to try to play tricks on you is you're going to see this as picking number 1. This isn't picking the number 1. I'm not starting it with a 1. It's just the number of choices. How many choices do I have for the first digit? 1. What's my choice? The 3. So unlike people, it gets a little bit tricky in your brain because we're dealing with 2 different numbers, but they represent different things. Is there any other restriction in the question? So how many choices for the second? And then how many choices for the last one? This is the identical question to Jack has to sit first. How many different pins start with a 3? 25 of them. How many are even? How many blanks? What makes a number or a digit even? Ends with a 0, 2, 4, 6, or 8. For our possibility for this, what could we end with? So you can either write even, or you could put a 2/4, whatever makes sense in your head. But you need to show me something that shows why one of these blanks is not going to be a 5. We do the restriction first, just like we did with Jack and Jill, so we have 2 choices for the last digit. Again, this doesn't represent I'm picking the number 2. It doesn't mean my digits have to be something, something 2. It represents choices, and I have 2 choices for the last spot. Does it matter for the first one? How many choices? Does it matter for the second? Total number of pins that are even? Again, this doesn't mean I picked the pin 552. I might have, but this is just representing choices. Why did we multiply them? Because it's and. You need a first digit and a second digit and a third digit. How many use only odd numbers? Okay. How many blanks? So you notice that's always the first thing you figure out is how many blanks. Now you figure out the restrictions. What's the restrictions? All 3 have to be odd. What's the difference from the pin being odd and using only odd digits? So if it was the pin that had to be odd, what would be the restriction? Just the last digit. Because this one says odd digits, all 3 have to be odd. How many odd digits do I have to choose from? Then? Why is it not going 3, 2, 1 like it did with the people? Because we can repeat them. 3 times 3 times 3, 27. How are we doing so far? Good, good. I think Maddie likes these questions. Let's do the number questions. Using only the digits 2, 3, 5, 6, 8, and 9, find the number of permutations possible in each situation described below. Repetition is not allowed. Highlight or circle the keywords in that question. What did you highlight? Repetition not allowed. I would probably do the numbers as well. Okay, let's read through the 3 situations. How many 4-digit numbers greater than 6,500 can be formed? What's key in the part A? 4 digits. And it's even italicized, so you know that's really important. Part B, how many 3-digit even numbers are there? 3-digit even. How many numbers less than 400 are there? Less than 400. Okay, first one, 4 digits. And we want it to be greater than 6,500. I'm just putting it up there so we remember the situation. 4 digits greater than 6,500. So this is actually a double restriction. First restriction has to have 4 digits. Second restriction, greater than 6,500. So what I do in my head is I just work through the numbers one by one. So I look at the first number. Can we start with a 2? Can we start with a 2 and have that be greater than 6,500? Not a trick question. Can we start with a 2 and have it greater than 6,500? No. Can we start with a 3? Can we start with a 5? Can we start with the 6? Okay, so case number 1 is going to be starting with the 6. If I start with the 6, is there a restriction on the second digit? So now I go back through the list. Can I have the 2 in the second spot? Can I have the 3 in the second spot? Can I have the 5 in the second spot? Can I have the 6 in the second spot? No, why not? Can I have the 8 in the second spot? Can I have the 9 in the second spot? What about the third digit? So as long as I have the 5, 8, or 9 in the second, does it matter what the third is? No, anything's going to be bigger than 6,500 no matter what I have here. So there is case number 1. So we talked about the 2, the 3, the 5, the 6, the 8. So let's go on to the next one. Can I start with an 8? So case number 2, starting with the 8. What about the second spot? Well, as long as I have an 8 here, does it matter what comes next? No, because it's going to be 8,000 something, so it doesn't matter. The last case is going to be what? Starting with the 9. I'm just going to go through that all again. All I do is I go in order, and I start with the first number and say to myself, can we start with a 2? No, because it won't be bigger than 6,500. Can we start with a 3? No. Can I start with a 5? No. Can I start with a 6? Yes. So that became case number 1. Because this has a 500 here, there was also a restriction on the second one, so I went back through the list. Can the second be a 2? No. A 3? No. A 5? Yes. A 6? No. Why can't I have the 6 here? Because that would be 6,600. Because we can't repeat, the question said 8, 9. Okay, then I went on to my next case. Can we start with an 8? Yes. Doesn't matter what comes after. Can I start with a 9? Yes. Doesn't matter what comes after. Okay, now let's fill it in. How many 6s do we have? Well, this is only the first question. How many 6s? I have 1. How many 5, 8, or 9s? Doesn't matter what comes next. So I had 6 numbers to start with. How many of them have I already used? 2 of them. How many numbers did I start with? How many of them I've already used? How many are left? Followed by? Okay, let's backtrack. A lot of people are going to think I used 4 numbers here because I have 4 numbers listed out. But this just represents choice. How many of them did I actually choose to go in the second spot? 1 of them. So even though I had 3 choices, I only picked 1. I can't put 3 digits all stacked on top of each other in the second place. How many 8s do I have? How many choices do I have for the second spot if I've now used the 8? Followed by? Followed by? How many 9s do I have? Choices for the second spot? If you wanted to, you can absolutely put these 2 cases together. If we wanted to group them, I would have my 4 blanks. I would have an 8/9, which would give me 2 choices, followed by 5, 4, 3. If you wanted to group the last 2 cases, you absolutely could. It's up to you. You cannot, however, group with the first case. Why not? Because this has a restriction on the second one. So if your brain likes to list them out as separate cases, great. If your brain can see these 2 can go together, great. But you cannot do anything with this case. He has to be himself because he's got a double restriction. Okay, a 3 times a 4 times a 3. If you do them separately, a 5 times a 4 times a 3. If you do them together, a 2 times a 60. So whether you have 60/60 or you have 120, it's the same. What do I do with the cases? Add them. So a 36 plus a 120, 156. That's as hard as the restrictions are going to get. There's a lot going on in that question. Anybody's brain hurt yet? A little bit? B. How many 3-digit even numbers are there? First you pick number of blanks, then you deal with repetition, then you fill, or restriction, then you fill in the blank. How many blanks? What's the restriction? Even. How do we determine if a number is even? The last digit. What are the choices to make it even? A 2, a 6, or an 8, I heard somebody say. How many choices does that give us? How many choices for the first blank? 5 followed by? Why is it not 3 if we had 3 choices here? So if we had 6 in total and I used 3 of them, why? Because I only picked 1. I put 1 in that spot. I had 3 choices, but I only physically took 1 number out of that pile. A 5 times a 4 times a 3? 60. 60 3-digit even numbers. Last one. How many numbers less than 400? Less than 400. I'm going to do exactly what I did in case or example A. I'm going to just go through the possibilities. Could we start with a 2? I heard you with a question mark at the end. Can we start with a 2? Does it matter what the second digit is? Does it matter what the second digit is? Oh, because it says less than 400. So 399 all the way down. Okay, so if I start with the 2, does it matter what the second digit is? If I put anything here, will it be less than 400? Yes. Okay, could I start with a 3? Can I group those or not group those? Can I start with a 5? Can I start with a 6? Can I start with an 8? Can I start with a 9? Okay, so all I did was just go through the numbers just like I did in part A. How many choices for the first blank? How many choices for the second blank? How many choices for the last blank? .40 with a question mark at the end. But does it have to be a 3-digit number to be less than 400? No. Are there 2-digit numbers that are less than 400? Okay, so we're going to have a 2-digit number will be case number 2. Marjorie, wake up. Does it matter what goes in the second digit? Or the first digit, sorry. So if I put a 2, a 3, a 5, is it going to be less than 400? How many choices? Followed by? For a total of? Could it be a 1-digit number? Case number 3. I heard 6. What do I do with the 40 and the 30 and the 6? Why? Because it's or. It's either 3-digit or 2-digit or 1-digit. How many numbers less than 400 can we make? 76. No question mark. Exclamation point. The exclamation point?